Question 2.8 in the textbook tells us to draw possible Feynman diagrams for the following two processes, process A and process B. Let's start with A. In A, we can see the decay of a muon into an electron, a positron, a muon neutrino, and an anti-electron neutrino. So right away we can see that there are neutrinos in this coming out as products of this decay. So we know that the weak interaction is involved here. So we can actually start drawing this Feynman diagram by starting with the charged weak interaction, which includes the a lepton and its corresponding neutrino, as well as the mediator for the charged weak interaction, which is the W boson. So let's start with that. Here is the muon going forward in time. And the other leg is a corresponding neutrino. So that's also going forward in time. Corresponding neutrino. And then the mediator for the weak interaction, which is the W boson, which we can represent with this wiggly line. There we go. And so now we can actually tick off these from here to help us keep track. So we've dealt with the muon and its corresponding neutrino. So what's next? Well, we can see that there's actually still another lepton and its corresponding neutrino pair. So that would be an electron and the electron neutrino. So we can actually draw another primitive vertex for the charged weak interaction like so. So we have an electron going forward in time. And then we have the its corresponding electron neutrino. However, this electron neutrino is an anti-electron neutrino, so we can represent that in the Feynman diagram as going backwards in time. So we can take those off. And lastly, we are left with the electron and a positron. So we can actually finish this off by coupling the W minus boson mediator with a photon. And we can do this because W minus boson is charged and it couples with the photon. So the electromagnetic interaction is actually at play here as well. So let's draw that in. Here is our here is our photon, kind of wavy. There's our photon, and the photon, or the primitive vertex for the photon, has two leptons coming out of it, two of the same lepton. And so luckily for us, we have the two of the same lepton. One is going forward in time, one electron, and another electron that is actually a positron. So it's the opposite, and so we can represent the positron as going backwards in time on the Feynman diagram. Now let us discuss the Feynman diagram for interaction B, which concerns the decay of the sigma plus particle to the proton and a photon. So right away we can see that there is a photon that comes out, so we know that the electromagnetic interaction is at play here. We also see that we have the sigma plus and the proton, which are a part of this process. So we can see that these are both actually baryons, and we know that baryons are comprised of 3 quarks each. So we'll be dealing with 3 quarks with the sigma plus particle and 3 quarks from the proton. So I think it'll be really helpful if we explicitly write out the quarks so that we can deal with them. So here is the sigma plus quarks. So a sigma plus particle is comprised of 2 up quarks and a strange quark. And the reason for this is because the up quarks have each have a charge of plus 2 over 3, and the strange quark has a charge of minus 1 over 3. So if you add them all together, it's minus 1 over 3 plus 2 over 3 plus 2 over 3. That'll give you plus 1, which is the charge on the sigma particle. Let us also write out the quarks for the proton. The proton is comprised of 2 up quarks, like the sigma plus particle, and the third quark is actually a down quark. And same reasoning as the sigma plus particle, plus 2 over 3 plus 2 over 3, and the down quark has a charge of minus 1 over 3. So that'll give us a total charge of plus 1, which is consistent with the charge of a proton. So the up quarks they act as spectator quarks and in this decay. And this is an indicator of the strong interaction at play here. So now we've included the decay of the sigma plus particle into the proton. So now we need to find a way to connect the last quark for the proton and the sigma plus particle. And we also have to tack on a photon at the end on the right side of this interaction. So how can we do that? Well, we have quarks of 2 different flavors here. And so our first instinct would be, okay, let's connect them together via the charged weak interaction, because we know we can do that. However, there's one thing that's preventing us from doing that, and that's the conservation of charge. So as I said earlier, the strange quark has a charge of minus 1 over 3, and the down quark has a charge of minus 1 over 3. So if we were to just connect these together, the charge would not be conserved. And so we know that this decay has actually happened before, meaning that charge is conserved. So we can't actually go about connecting both of these together in a primitive vertex with the charged weak interaction W boson as the mediator, because charge won't be conserved. So instead, we're going to take a bit of a detour and introduce an up quark to balance the strange quark and the down quark. So what we're going to do is draw 2 legs like this, and then have an up quark in the middle. Oh, by the way, I should write this. So this strange quark is going forward in time. This down quark is going forward in time. And so the up quark has a charge of plus 2 over 3, which will counteract the minus 1 over 3 and the minus 1 over 3, and have a conservation of charge. It'll all turn to 0. So all is nice and dandy, and now we actually have a quark of one flavor, a quark of another flavor, and we can connect them in a primitive vertex via the charged weak interaction, like so. So here's a squiggly line, and then another squiggly line. Very bit ugly, but it'll have to do. So there's our W minus, and we can wrap this up all nicely by including the photon, because that's really all that's left, right? And the photon will be swinging like this to the right, and there you have it. You have the sigma plus decaying into the proton and a photon. Excellent.